the end a little bit early today, so we can, if there's any questions about the exam,
Okay.
we'll see how it goes. So the first thing I wanted to do was just discuss since we already calculated the states of the infinite square well. So I'll just remind you that the states were the normalized states. Psi n of x are the square root of 2 over a, the length of the well, times n pi x over a, and a general state inside the well is given by some psi of x. It's just the sum over the states. So just the spatial part of the wave function is just a sum over those states. And so we should demonstrate that the states are in fact orthogonal and orthonormal. So what we need to show is that the inner product between psi n and psi m is equal to delta n m. And so we can do that by writing this in terms of an integral. So psi n psi m is equal to the integral over dx using our notation for the completeness relationship. So this is psi n x psi m, and this then is just the integral dx. This is psi m, and this is psi n star of x, psi n of x. And now the integral will just go from 0 to a, because the wave function is 0 outside the box. So we have to show that this integral gives you this delta function, or this Kronecker delta, sorry, in m. So to do that, we can write the prefactor, that's 2 over a, and then the integral 0 to a, and we'll, instead of writing sines and cosines here, we'll use the exponential. So for the exponential, we'll have 1 over minus 4 times e to the n pi x over a minus e to the minus I n pi x over a times e to the I n pi x over a minus e to the minus I n pi x over a. So the minus 4 just comes from the 1 over 2i from each factor of the sine. And so we can just multiply this out. So that's 2 over a, we've got a minus 1 over 4, integral 0 to a, and now we can write this, and we'll have, just expand this out. So we'll have e to the I n plus m pi x over a from this term, and then we'll have a plus e to the minus I n plus m pi x over a. And then a minus sign. So we'll have a minus sign for this term and this term, and this term will give us an n minus m, e to the I n minus m pi x over a, and then a minus e to the minus I n minus m pi x over a. Okay, and now this term here will be, this is just going to be twice the cosine of n plus m pi x over a, and then we'll have a minus. This term here will give us twice cosine of n minus m pi x over a. Okay, and now the rest is just some simple integrations. So let's look at the cases. So there's two cases. So what about n equals m? So if in the case that n equals m, this will just be some other integer, and it's a cosine. And when we integrate the cosine, we'll get a sine. And that sine from 0 to a will just give 0. But this term, if n is equal to m, this cosine gives us 1, so that just gives us a minus 2. So we'll have a minus 2 integrated over the interval will just give us minus 2a. So this will give us, this would be equal to then 2 over a 1 over minus 4 times minus 2a, and that's just equal to 1. Okay, and then in the case n is not equal to m, this again just gives us some integer that integrates to sine and goes to 0, and this also gives us just some integer that integrates to sine and goes to 0. So it's just 0 in this case. So we do in fact have orthogonality of those basis functions. Okay.
Wait, is this just because if n, what is that? So you said so n is equal to m, then the function, the entire function is equal to 1. Oh, because the n minus m gives you. Okay, I see.
This is the only contributing term if n equals m.
Okay.
Because cosine of 0 is 1.
Right.
Yeah.
Okay.
All right. Any other questions? Okay, so sines and cosines are orthogonal like that. And so what that means is that when we write functions for, this is just like when we had other quantum systems here of a spin or whatever, we could write it in terms of a linear combination of these orthonormal functions, and that's how you should think about the states, just as linear combinations of these orthogonal basis functions. So let's look at an example. So we know that the base state here, the ground state, psi 1 of x is n equals 1, so it's just pi x over a. It's this sine function. But I could put, suppose the state is initialized in the infinite square well. Suppose it's initialized as a parabola. Okay, so I'm going to draw it. It's going to look the same here. But suppose that psi of x is equal to some amplitude, and then I need some function. I need a parabola that fits in the well. So I can do that by, it has to go to zero at zero, and it has to go to zero at a, so we can just write x, and then a minus x. The coefficient of x squared has to be negative because it points, or it opens up downward. Okay? So now I can ask, what is the expansion C1 psi1 of x plus C2 psi2 of x plus C3 psi3 of x, and so on. Okay? So I'm asking which basis functions are represented in there. So let's make a guess. Let's see what your predictions are. All right, so what's your guess?
Do you have to do a Taylor expansion?
No, well, this is like, think of it visually like this. So this is psi of x equals C1 psi1 plus C2 psi2 plus C3 psi3.
Oh, I see. So they need to interfere in a way that just produces a parabola. Okay.
Well, it's big. Oh.
So C1 is going to be, I would assume, the biggest one.
Yeah.
And
What about C2?
I'm gonna let me say 0.
There is negative. There is negative.
So like, I'm gonna guess that you're only gonna have values for like odd integers, or like the odd c's and the even c's are all gonna be 0.
Yeah, good, that's right, yeah.
Let's see.
So let's guess some numerical values.
All right, A. C1 is A.
No, we'll normalize for A.
Okay. C1 is 1.
Well, it's not exactly the same thing, right? I mean, that parabola is not exactly the sign, so
Right,
it's
okay.
not gonna be exact.
Half.
No, you're close with the first time.
Dang. Is it A over 2?
No, A's out of the picture.
No, A's out of the picture.
We're gonna normalize and get rid of the A. But just based on the picture, what do you think?
Is it a sign?
No, it's a number, just a number.
Or just
C,
a
C1,
number.
2, and 3 are just numbers.
2.
No, you know that you have to have, remember, you have to have the sum of the coefficients squared, mag squared, it's have to be 1. So it has to, that's the sum up to 1.
It has to sum up to 1. Okay, I see.
Oh, then, wait, so 2
Square
is 0.
1 over root 2.
No, you were really close the first
I was
time.
I was close when I said 1.
Almost, yeah, okay. Let's
I mean,
just
I was
say
thinking like 1, a half,
well,
and
I
a
mean,
third.
I was wanting to pin you down to some, digits here. But,
Okay.
You wanna guess any digits?
Guess any digits after 1.
No, it can't be greater than 1. It has to be a number.
I'm so confused. So my first guess was A. And my second guess was 1.
So 1 over square root
How close is
2.
it? How close does it look?
It looks kind of close.
So, I don't know, 80%, 90%, what do you guess?
I see.
8/10.
80%.
I was thinking 0.5. I'm thinking half. It's halfway there.
Anybody else?
0.717.
So we've
This
got
Price is Right
0.8
rules.
and 0.5. Anything else?
Oh, I said 0.7.
5. You know what? Hail Mary. 5 over 10. Golden ratio. 5 over 10.
Okay.
But how smart would I have looked if that was true?
Well, what about, okay, C2, you said 0.
Yeah.
Somebody's, okay.
It's got to be 0. I'm assuming.
And then what about C3?
Say it's half as much as C1.
Does this look like this?
Not even close.
No. Hmm. Oh, is it negative?
So it's got to be
No,
like,
not negative.
it's got to be really small then.
Gotta be small.
It's got to be really
Point
small.
2
Okay.
to go with my 0.8.
Well, okay, yeah, but remember, it's the square, sum of the squares.
Oh, yeah.
Squares.
Then
Okay, so is that, okay, those are the guesses then?
Yeah.
So what you do here now is just normalize, normalize psi to find A. So, this is just then mag A squared from 0 to A of x squared A minus x squared dx equals 1. Right? That's just psi star psi, and I'm integrating it to get 1. And this is just an integration you can do. This is, what is this? That's x to the 4th minus 2a x cubed, and then plus a x squared dx equals 1. Okay, and so this is just a polynomial,
Yeah.
simple. So you'll find that a here is equal to mag a squared is 30 over a to the 5th. Okay, and then what we want, so we have psi of x is equal to 30 over a to the 5th times x, a minus x. So that's the wave function here. And we want to calculate, if I want to calculate any of these coefficients, I just have to take the inner product of these different wave functions, right? With the basis states. So C1 then is the inner product of psi1 with overall psi. So
Right.
that's the integral from 0 to a of the sine pi x over a times our wave function here, which is 30 over a to the 5th x a minus x. Okay, so you just have to do this integral. And you can do it by hand, but, you know, for the sake of time here, I'm just going to show you what it is. I'll give you the numerical result. This is, you guys ready for this reveal?
Yeah.
Okay, give us a review.
0.99928.
That's why you said I was closer with 1.
I see.
It's almost 1. I see.
Okay, so then we have mag C1 squared is equal to 0.99856. So that means that the probability you would find it in state 1 is 99.8%.
Oh, man.
Right, so if okay, so C2, if you calculate it, it's the same function except you have a 2 here in the sign.
It's crazy that's I guess that's independent of A.
Well, I mean, we calculated A.
I'm at little a, the width of the box.
Oh, right.
Yeah.
C2 is 4 times 10 to the minus 17, which, you know, if you, the error in the floating point precision
Yeah.
for, you know, a calculation is in a computer for, you know, something that's got the precision that's in your computer is roughly about that, so it's pretty much just 0. And then C3 is equal to 0.0370. So that if we look at the magnitude of C1 squared plus the magnitude of C2 squared, or just C3 squared. So if we have to square that.
So C2 isn't 0, it's just nigh indistinguishable from 0.
Yeah, right. Yeah.
Okay.
So C3 squared, sorry, I didn't write it. C3 magnitude squared is 0.00137. Okay, so you will have, there's this very, very tiny probability, 0.1%, that if you measure the system, you would find it in the third state. And then if you sum, if I'm summing these two probabilities, C1 and C3, this gets us really close to 1. It's 0.99993. Okay?
Are there more, because you put ellipses out in the psi of x, so like if you did this to C n to approaching infinity, you'd get 1 if you add them all up.
Right.
Okay.
Yeah, I mean, I think, C5 is gonna, I don't know how many more 9s you'll get here.
Yeah.
So it's pretty much,
It rapidly approaches 1.
right, so, the point is that this wave function here, if it looks like this thing, then, the decomposition is really straightforward, just as far as what you should be able to just look at it and see what you're gonna get, basically. And the other thing is the energy is obviously really close. If the wave function, is 99.8%, like the ground state wave function, then it should have an energy that agrees with that, and it does. So it will give you the ground state energy, essentially for the same ground state energy as for the first excited, or the ground state. Okay.
Okay, hold on. So you said that that C1 is a ground state?
C1 is the probability, C1, the
Okay.
magnitude C1 squared is the probability
probability.
that a measurement would find you in the ground state.
So these are energy levels, not just like arbitrary states.
Yeah, I mean, these states have energies.
Okay.
Remember, that was n squared,
Yeah,
pi squared, h bar squared over
I remember now.
2ma squared.
Okay, so like, are there any like, can you give an example of like a real world system that does this, where like you basically only expect to really see stuff in the ground state, but then
I mean, that's,
like an excited state basically doesn't happen, but then the excited state above that, there's a small probability that it can be there.
Yeah, I mean, the color centers is
yeah,
an
the
example.
center was.
You don't have this kind of a state, but it's kind of close. In fact, this arch here doesn't really have to be that, for this kind of a system, it's so simple that it doesn't really make much of a difference, because this function looks very much like this function, but you can also calculate it for, you know, if you put in this, just a triangle wave instead of that arch, this triangle wave, if you normalize it, will also give you an energy that's close to the ground state. It'll be more different than this one because it looks less like the actual ground state.
I see. Okay. Right, the colors in this, I forgot about those. Okay. Hey, dude.
Hmm?
Are your videos available on campus?
No, they're all on my hard drive now.
Would you mind sending it to me? Really? Oh, they're on the hard drive.
Mhm.
Yeah, okay.
I mean, if you got some you want in particular, I
Yeah,
could
'cause you-
upload it to YouTube.
Okay, I was gonna ask. Or like a Google Drive or something.
Do you have, are they, you can upload them.
I mean, yeah, I have all of our lectures except one on my hard drive at home. So yeah, I could upload them. It'd take me a little bit.
Yeah, if you don't mind, I would like the last,
Yeah, send me a link if you do.
including this one, last three,
All right.
if you don't mind.
All right, so the next thing I want to talk about is, we're going to kind of continue on with this, the square well. But I want to talk about bound states versus scattering states, and we're going to focus on bound states for just a little bit. So, let me draw a picture again of a potential. So if this is the potential V of X and we have an energy, we talked earlier about having these classical turning points. On both sides of the potential, and that's where a classical particle, if you had it in this potential, it would just roll back and forth, and it would turn around at each point there. Okay, but there are other kinds of potentials where the particle could escape. So we want to define what's different between a bound state and a scattering state, and so let's bound states. Scattering states. So bound states are states where a classical particle would be stuck. Okay, and in this case, just like we saw with the infinite square well, we get the boundary conditions give quantization of the energy levels. So this is a discrete okay, so you can number the states in a system that's bound with a discrete set of integers, and you know, just as the infinite square well has. And then in the scattering states, for a scattering state, the classical particle could escape. And for these particular states, the index that gives you the you know, the energy is a continuous number. Okay, so this is like a free, a free particle can have. So in a free particle, we have h bar squared is equal to, sorry, E is equal to h bar squared k squared over 2m, where k equals 2 pi over lambda is a continuous variable. Whereas, for classical states here, we have some formula for it.
So, and this is because you're talking about, you said classical particle, but that last part, like, this is in quantum mechanics.
Right, so, but, yeah, I mean, we're calculating it quantum mechanically, but we can, for example, we could have a situation like this, V of x. If we have an energy here, the particle will just roll down and will escape, for example. Okay. So that's a continuous.
So there are continuums in quantum mechanics.
Yes, yeah.
Okay,
Free particles.
interesting.
Okay, and then another example is if we have an energy up here, a particle impinging on the barrier can just, classically, you can just go over it. Okay, so now that we make that distinction, let's look at the square well. Let's take the square well and let's shorten it so that it's finite. Okay, so let's draw it like this. So this is the finite square well. This we'll say is the zero potential energy, so this is minus some V0, and then we want to look at an energy here that's also negative. Okay. So classically, what do we have? We have, if this is the energy, the particle can't escape the well. So this is a bound state problem. Okay, so as long as that E is less in magnitude than V0, then this will be a bound state problem. Or sorry, E is just, as long as E is less than 0. That's a bound state problem. Okay, so let's put the regions in that we wrote before. So regions 1, 2, and 3. And then we want to solve the Schrödinger equation. In each region. Okay, so what does the solution have to be in regions 1 and 3?
Exponential decay.
Right. It has to be exponential decay, and we can write down, so in 1 and 3, we'll just write down psi 1, for example. We'll have minus h bar squared over 2m psi 1 double prime of x has to equal, now v is 0, and then we have minus the magnitude of E times psi 1 of x. Okay, so that means we can write, we'll define, psi 1 prime of x is equal to 2m magnitude of e over h bar squared times psi 1 of x, and define, what's this double prime? Define kappa squared is equal to 2m magnitude e over h bar squared. Okay, so we'll use kappa. So in region 1, now in region 1, let's give it an amplitude b. Let's call it b e to the plus kappa x. It'll be plus kappa x because x will be, if we put the origin of our coordinate system in the middle of the well, and this is, the well has a width of 2a. So that's minus a to a. Then psi 1 will be plus kappa x because x is negative. And then psi 3 of x will give it an amplitude of f e to the minus kappa x. Okay, so we've already found 2 solutions. Now, I also mentioned before that when we, what we're going to do in order to solve the problem completely, which means find all of the amplitudes and things like that, we'll have to match the solutions at the boundaries. So in the middle here, which we will have an oscillatory solution, and then it has to match up on the boundaries to this exponential decay. And so at the boundary, at x equal a, we must have psi 2 at a equals psi 3 at a, and psi 2 prime at a equals psi 3 prime at a. And there's also a set on the left-hand side as well that you have to satisfy. So let's now do region 2. Okay, so we'll have minus h bar squared over 2m. Well, let me write down the Schrödinger equation again so we don't, it's minus h bar squared over 2m psi double prime of x plus v of x is equal to e psi of x. Okay, so for region 2, where here we have a v is non-zero, that's v psi of x. So in region 2, we have h bar squared over 2m psi 2 of x double prime is equal to, now I'm going to move my v to the other side, and but I remember that v is actually, it's negative, so I'll write it in terms of the magnitude so we know. So this will be the magnitude of V0 minus the magnitude of E times psi 2 of x. Okay, when I do these problems for these finite well problems and the different well problems, I always use the magnitude sign so I know what's positive and what's negative. Okay, it really helps. So it keeps me from getting confused. All right, so now we can write psi 2 double prime of x, and we're gonna define another variable here. So this is h bar squared. I've got a minus sign in front of it now because v0 is larger than e. So this is how you know for sure that it's in fact the overall coefficient is negative, and so that it has an oscillating, so that it's oscillating solution. So now let's define L squared as 2m mag v0 minus magnitude of v over h bar squared. Okay, so when you're in these different regions, there's also a convention here that if you once you look at enough of these problems, you'll see it. Whenever you're in a region where it's oscillatory, people will use K or L or something like that, just letters from the regular alphabet. And then when you're in a region where you're in exponential decay, they use kappa and things like that, so or alpha or some Greek letters. Okay, so that'll also help you when you're working through these problems. These problems can get very tedious sometimes. All right. So we now what are the solutions to this thing? We know it's oscillating, and now we can just we know it's sines and cosines, so we can write down our solution. It's psi 2 of x, and we'll give it coefficients of c and d. So let's do c sine L times x plus d cosine L times x. Okay, so there are two sets of solutions here. Even and odd, like in this, just like in the infinite square law. Okay. But let's just, for the moment, let's just look at the even solutions. So that means if we're going to take the even solutions, the cosine in the well, right? The cosine in that well is going to be, if this is x equals 0, the cosine is going to be, that's going to be the cosine. And the sine will be, let's see, that's the sine solution. Okay, so let's just look at the even solutions first, which will have c equal to 0. So now let's use these equations. Okay, so what's psi 2 of a? So psi 2 at a, if c is 0, will be d times the cosine of LA. And that has to equal psi 3 at a. And psi 3 at a will be f e to the minus kappa a. That's the first equation. And then we have to take the derivatives. So if I take the derivative of this thing, that's going to be minus sine L, minus L times sine L, LA. So this will be minus DL sine LA. And then the derivative of this will be minus F kappa e to the minus kappa a. Okay. All right, so these are the two equations at the boundary. And this is enough to tell us about, we have, inside the well, we have this L, which, you know, that L is what gives us the frequency, it's the wave number for the wave inside. And then kappa tells us how quickly this thing drops to zero. Okay? And they're both related to, both L, kappa has an E in it here, and L also has an E in it here. So what we get from these two equations now is a relationship between kappa and L. And that's what we want to, exploit. So I can, if I just look at these two equations, the first thing that comes to mind is why don't I just divide one by the other so I can get rid of my D's and F's. So if I do that, I'll have minus L sine LA over cosine LA is equal to minus, F's will go away, just minus kappa. Okay, so so we have tangent LA is equal to kappa over L. All right. So now the problem is this is not a really simple equation. You can't really just solve it. So we're going to solve it graphically. There's no, closed form solution for it. So let's see what the solutions look like. So in order to investigate this equation, we're going to define several different variables just to make it easier to get through. So let's define z is equal to L times A, and then we'll have the tangent of z is equal to kappa A over z, and we want to rewrite kappa A here. So kappa A is equal to, what, it's that. Let's do kappa squared A squared, because I know what kappa squared is. It's 2me over h bar squared. So we'll have 2m magnitude e over h bar squared times a squared. And now let's look at L squared a squared. L squared a squared is 2m over h bar squared magnitude v0 minus magnitude e. So if I add these two together, I've got a minus e, well, there's an a squared here. If I add these two together, I can get, these terms will cancel, and so I have kappa squared a squared plus L squared a squared will be 2m over h bar squared magnitude v0 times a squared. Okay.
So what exactly are kappa and L?
Kappa is it's the constant that comes out in front of taking the second derivative, so it's the solution, the solution is given by e to the minus kappa x over in this region.
Right, but it's interesting.
So it's the rate of decrease of the wave function amplitude.
I see, because it has units of, what is that, 1 over x?
Yeah.
So, okay, so it's a rate of decrease, but instead of a rate in time, it's a rate over space.
Yeah,
Okay.
that's right, yeah.
Okay. So then, I see, okay, I get it.
Yeah, and L just, L, it's the distance between, the potential and E, that's,
Right.
that's L,
Okay,
or L squared.
all right, thank you.
Yeah.
Yeah, no, sorry, just, it's really hard for me to do math if I can't like visualize in my mind exactly what's going on here.
Oh, sure, no, that's good. Okay, so let's define, so we said that LA was Z, so we've got here that kappa squared A squared is plus Z squared, and we'll define this now as Z naught squared. Okay, I'm just gonna define all that stuff as Z naught squared, and now I can plug kappa A into this thing, so kappa A is equal to Z naught squared minus Z squared square root. And I can write this as, I can pull out a Z and write it as Z naught over Z minus 1. Z naught over Z squared minus 1. Okay, so that, if I write it like that, then we have tangent of Z is equal to, kappa A's got a Z in it there, so this Z will be canceled by that Z. So we can finally just write this as Z0 over Z squared minus 1 to the half. Okay, and that's what we want to plot. So let's plot this thing. So if we plot Z, so if I plot the left-hand side, it's tangent of Z, right? Where does tangent blow up?
Pi over 2, right?
And
0.
It's all.
Negative
all,
pi over 2.
Yeah, it's all integer multiples of pi over 2.
right,
Yeah.
integer multiples, pi over 2.
I'm trying to remember what it looks like.
So we've got pi over 2, let's see, that's pi over 2. I want to draw this correctly so it looks right. So then this would be pi, and this would be 3 pi over 2, 2 pi, 5 pi over 2. Is that right?
Yeah.
Okay, so the tangent blows up, so there are some asymptotes. So I can get rid of these. All right, and this just goes on. So that's the left-hand side. The right-hand side does what? Z0 squared, this is a positive number, right?
Right.
Z0 squared over Z. So at what happens at very small Z?
It blows up.
Yeah.
It goes to infinity.
Right, it's coming in, it's coming down from like infinity. So this comes down like this, and then whenever it reaches 1, it hits 0. So this function is z0 minus z squared minus 1 square root. And this is right when z0 over z equals 1. Okay, and so the solutions are wherever they cross. Here, here, here. All right, now, so if you want those energies, you have to calculate them numerically or from the graph. But let's look and see what happens. Let's just use some intuition now. What does this graph look like if the well is very deep?
If the well is very deep, does that make?
What kind of solutions do you expect? So, now we're looking at the well. Suppose the well looks like this.
So it should look like an infinite square well.
Right.
So
So that means you're gonna have a lot of states until you get close to the top of the well. Okay, so what this picture looks like is,
So it's a lot more
be a lot more
solutions.
Yeah.
yeah, I mean, you've got, I'll just,
So it's got a further path to drop.
Yes, it takes a longer time before it drops off.
So then
it'll come along and look like this.
Look like it's just like a straight line going across.
Right. And so you'll have, the distance between these things is identical, and that's gonna give you some regularly spaced, well, that'll give you energies that look like the infinite square well. So if we have, here, the Zn, there'll be something like n pi over 2. That's where the crossings will be at this. They'll be at n pi over 2 in z. And so if you calculate, if we have z squared then it's 2ma squared over h bar squared v0 minus e. And we have, this is n squared pi squared over 4. And this is approximately 2ma squared over h bar squared v0 minus e. And now we can solve this thing for e. Or let's solve it for minus e. So I can write it like this, minus e, so the n is equal to minus v0 plus n squared pi squared h bar squared over 2n times 2a squared. just solve this thing for E. And that 4, you can stick with the A and make that 2A. So this is the well width. And that looks just like the, I erased it for the infinite square well. Remember the infinite square well energies. If that was the well width.
So what do those solutions mean again? Is this like where K equals L, or like what does it mean to have a solution at those points?
So the relationship that we had, which relates, the energy to this discrete set of solutions,
Right.
is from the boundary condition. Again, remember when we did the infinite square well, it was the boundary conditions again that gave us the quantization.
Right. Okay.
That's all we're doing here. We just have, our boundary conditions now are just the set that the wave function has to be equal and
Right.
the derivative of the wave function has to be equal.
Okay.
And so that gave us this relationship between the L and the kappa.
Yeah.
And that's what determines the energy relationship. So you'll get to do this numerically next semester if you take the computational course.
Oh, good.
Yeah.
It's fun.
Will we do it, or will a computer do it?
The computer does it. It's just fun to work it out.
Alright.
Okay, are there any questions for the finance area? Okay, I think that's a good stopping point, actually. So I wanted to remind everybody about the exam tomorrow.
Thursday.
Thursday.
It's Thursday, thanks, sorry.
Like what?
Oh,
Just-
wait, sorry, hold on, before you erase that, let me,
Oh, yeah,
yeah,
okay.
let me get, since, Zach's not here